Is there a way to tell?
Yes.
Awesome. OK. Hi. It's a small group, so if people have questions, interrupt me. I had no idea really what the mix of backgrounds would be, so this may be either too high level or too low level. I'm actually coming from LinkedIn, where I've been for a long time, like the last 7 years. And I worked there on data infrastructure primarily. So I worked on a bunch of things from kind of the early days, but spent at least the last 3 years pretty heavily focused on the data infrastructure that kind of ran the website and shuffled data around. A lot of what I'll talk about is kind of ideas and systems that came out of the problems we had there. And I'll kind of motivate those. Recently, as was alluded to, I actually left LinkedIn and I'm starting a company which is actually related to some of these ideas. And I'm happy to answer questions about that as well. So I'm going to talk about a couple different things. I'm going to talk about the problem of data integration, which is not something people talk about that much. I'll talk about Apache Kafka, which is a system we built, which is kind of related. And then I'll motivate kind of why we built this system and the problems it's useful for. So let me start with data integration. This is my favorite problem. A lot of people would call this ETL. So just so that I ground myself, have people heard of like ETL? Yeah, everybody knows. OK, ETL, everybody knows ETL. All right, so this will be an easy one. All right, so ETL is you want to get a copy of your data into your data warehouse and kind of munge on it for analysis. This similar problem kind of exists all over the place. And it's actually one of the bigger problems for any kind of large company running a bunch of different systems is putting everything together and making sense out of it. And it's a problem that I kind of fell into without a lot of understanding. And I'll talk a little bit about why I think it's important. This is Maslow's hierarchy. I guess no business presentation is complete without Maslow's hierarchy. I don't know how many people have seen this. This is supposed to be some hierarchy of human needs, starting with your physiological needs like food and water, and moving up to kind of like self-actualization and the respect of your peers or whatever. And the point of this hierarchy is when you are lacking food and sleep and safety, you don't care about anything above it. And so my belief is, a lot of the use of data, like there's a lot of companies that are struggling to use data effectively. There's this kind of like big data movement. Nobody knows exactly what that means, but it has something to do with collecting and using data. There's some kind of similar hierarchy. The base of this pyramid is actually being able to kind of capture and instrument what is there. The next thing up is, what the hell does this mean? Like, are we able to keep track of what all these fields mean? And then everything above, like understanding automation. Like we eventually, had a bunch of sophisticated processes at LinkedIn that predict people you might know, or come up with similar profiles or whatever. But all of that is built on like, actually having the data and being able to make sense out of it. And as I spent time in this area, I found that there was more and more problems down towards the bottom of the pyramid. And I think the further afield you go kind of in the world, the more that's true. So a lot of people are very interested in who are kind of getting into this big data stuff. They're very interested in kind of, how can we apply deep learning algorithms to do whatever? And they basically don't have any reliable data flow to apply anything to. And of course, the algorithms do not produce correct results when fed incorrect data. That has remained true in computers. So the reason that this problem has gotten harder, the reason it's not solved out of the box is really two things. So first of all, companies are interested in new types of data. So if you were to ask a company what their data was, maybe a decade or so ago, they would basically go through their database tables, right? So they would say, well, we've got a users table, we have a products table, we have orders. This is our data. The set of things that people consider data that's valuable about the business has expanded dramatically. That includes a bunch of things you would call event data. So for a website, that's clicks, impressions, page views, whatever. But almost any kind of business has some events about what's happening, not all of which are represented in the current state of your database tables. And then this kind of machine data, which is again for the website use cases, application metrics. What is the CPU load across all these servers in a data center. And application logs. This is, again, kind of events for machines. And so the problem with these types of data, they're much larger. And the more traditional data systems are not built to address them. The second thing is really the explosion of systems, right? So these are things which are at LinkedIn that we were running. These are kind of our primary data systems that we made heavy use out of. It's different for each company, but there's kind of a multiplication of these things. Hopefully, at some point, there'll be some amount of contraction, but nonetheless, it's pretty diverse. So we had some things that were basically key value stores. We had something which was a kind of distributed graph engine that would answer queries about who's connected to who and what are the paths between people. We had an analytical store that would do the kind of like, real-time reporting, like counting things, basically. We had a search system, which is how you search for people. And we had a whole kind of real-time monitoring layer. Then we had the offline world, which was mostly Hadoop and Teradata. And as these systems started to evolve, this is kind of the world we started ending up in. So you have these different, at the top, different sources of data. At the bottom, these are kind of different destinations for data. And very slowly, you start to kind of piece together these pipelines that ship data from one thing to the other. And as you get to some scale, each of these little lines actually gets a little bit complicated, right? The data volume becomes large. You're potentially shipping data around the world, right? Because you're operating out of multiple physical locations. There's different kind of requirements. Typically, a data warehouse is more of an offline, load of data, whereas a lot of these other things are much more real time. And you kind of get to this full connectivity where you have something on the order of n squared pipelines that you're building between systems to shuffle data so that you can say search your logs and search the people on LinkedIn, but also get that same stuff into Hadoop. And that becomes this kind of increasing set of complexity where every system kind of ends up knowing a little bit about every other system. And the solution we came up to, we came up with for this is really a kind of central log, and I'll talk about this idea where everything kind of gets represented as a series of changes in this log, and these changes are each kind of structured record, and so everything in the business is in some sense a series of structured changes, and so that would cover at LinkedIn, that would cover everything from the page views that were occurring, error messages in different applications in the data center. If you restart a machine, hey, that's a message. Changes to databases. And that stuff would flow out into search indexes. It would flow out into monitoring systems. It would flow out into real-time processing systems. It would flow into Hadoop, where you can run kind of like big batch jobs on it, and it became this kind of central distribution point. And that system that kind of handled all that log box in the middle, is called Kafka. And so I'll talk a little bit about what it is and kind of where it came from. It's a little bit hard to describe. We basically implemented a kind of distributed log. We call it usually a messaging system because people are more familiar with that as a genre of infrastructure. So at a high level, you have this cluster of machines, which is acting as kind of a middleman, and you have producers, which are people sending a stream of messages, publishing messages. You have consumers who subscribe to that data, and you would organize it, we would say by topic. So you might have page views is one big stream that people are subscribing to. And for a while, this was kind of alone as a weird infrastructure thing. But actually, Amazon and some of the other cloud service providers have created similar systems to offer kind of as a service in the cloud. So if you're in Amazon, you can use Kinesis. It's pretty similar, actually, down to the APIs as Kafka is. So it's becoming almost a class of things. And I can talk a little bit about how we got here, how we came up with this idea, and how the infrastructure evolved. So like I said, we were kind of starting down this path of building these custom pipelines. I was managing one of the teams that was building one of them, which was really for the Hadoop cluster. And I was managing another team that was building another one, which was for this key value store we'd made. And so it was just kind of weird that we were hiring people to shuffle data on two different parts, and they're kind of doing the same thing. And at the same time, we had kind of increasing requirements to be able to do processing of data more real time, right? So stream processing or reacting and computing things quickly. And so that was how we thought, well, instead of having 3 projects, we should probably try and combine these in some way and come up with this central feed. And we went through a series of kind of trial approaches where we got different messaging systems, and we kind of benchmarked them, and we would like fork off some of the production traffic and try and run it against it and see if that would work. And we found, well, they weren't really designed for this kind of thing. And in particular, almost nothing was designed to be able to feed into an offline system like Hadoop, right? So in the Hadoop case, that system may go down for a period of time and come back after maintenance. In the meantime, you're buffering up everything that happened in some large-scale web company to feed to it. So none of our solutions worked. And then we started down the slightly crazy path of like making our own messaging system that would hopefully share some of the properties of the different ad hoc solutions we had, because each ad hoc solution was good at least one thing, So some were reliable at delivering data, some were low latency, some were high throughput. They each had to nail at least the one problem that they were there for. And we thought, well, it must be possible to make these things work together. And the basic design principles we had was, first of all, one pipeline to roll them all. We wanted to take the union of these requirements and try and put them together instead of making things, a bunch of ad hoc kind of bubblegum and duct tape solutions. We try and make one thing that was good, that was both durable and high throughput and low latency. Second of all, we wanted it to be a good basis for processing, not just shipping data around. So very often it's the case that you have to transform data that comes around. That's like simple if you can do all your transformation in a single process, but if you have to be able to split the processing up, then you need some kind of partitioning model and so on. And finally, we wanted something that was managed as a cluster, right? So I guess kind of the nature of modern systems is you want to kind of think about it, write to it, operate it, configure it as a cluster rather than as an individual machine like you would with a MySQL database where you kind of tune one database and then another application has another database. Much nicer is something where you can think of like a distributed file system. You don't really think about which machine you're writing to. And that makes it obviously much easier to run at scale. And so what that meant we had to do was, we had to be able to provide scalability, kind of like a file system, because if we wanted to replace these logging use cases, usually the way people are doing logs is they write it to the file system really quickly, and then they kind of ship this log off somewhere eventually. And so if we wanted to replace that use case, it had to be fast. It had to be efficient in terms of megabytes per second. We had to have guarantees that were good enough to handle the database updates that we had. In other words, we had to be able to guarantee that if you update your profile, we wrote it to the database, that update would get shipped into the the data warehouse or the search system, and it would get there. Didn't have to get there all in one giant transaction, but it has to get there pretty quickly, and it has to get there. It can't remain permanently inconsistent. So that meant we had to have some guarantee around both the ordering of updates and then also not losing updates in the system. And I already talked about making it distributed by default, which means having a partitioning model, having replication amongst servers. So if you do a write and a machine fails, you don't lose your data. This kind of stuff is just really required to make a system like this operable, right? You need to be able to go in and restart machines and not worry too much about what's happening at the application level while you're doing that. And so over time, this became heavily used at LinkedIn. At any given time, there's probably now this is a little older, but maybe a couple hundred terabytes of in-flight data that's kind of being shipped around. We replicate between the different data centers that we serve out of and the offline data centers where we would have Hadoop and this kind of batch warehouse processing. The load is pretty high, both in terms of reads and writes, and there's tens of thousands of processes that are connected to this that are publishing or reading messages. All right, so that's kind of Kafka. Let me talk about kind of what the abstraction Kafka presents is, and how it comes into play in our usage. So what Kafka provides, I said, is kind of a log. And so I guess I should start and kind of explain what a log is. Many people may already know this. It kind of depends if you have a systemsy background or not. I guess most programmers, when I talk to them, if you say log, they think really like a text file with a bunch of updates in it. I guess that is a log, but I mean it more in the kind of commit log sense of a structured, ordered list of records that have been appended in some kind of order. And so this is the abstraction that Kafka provides. It's basically a series of changes. You are always appending to the end. The records are immutable. They have some kind of sequence number that identifies them, and you usually read from the left to the right. Obviously, left to right is kind of a made-up thing, but we'll say it's left to right. And then because we are kind of having lots of logs, right, one for maybe page views and one for changes to this database and one for errors and so on, and because some of those we're going to want to scale quite a lot, we actually provide a partitioning model. So at LinkedIn, every page view, there's a topic called page view, which is actually made up of a bunch of partitions. Each partition is a log. All right. So that's the abstraction that Kafka provides. Most people don't. I also said it was a messaging system. Most people don't think of logs as a way of doing messaging, but they are actually not a bad way of doing messaging. You can think of the publisher or the data source as doing writes, which are appending to the log, And then you can have any number of processes which are reading. And you can think of each of these readers as being caught up at some point in time, right? And time here is really just this deterministic sequence number that we're keeping with the log. And so if you go back to our horrible picture with all those different systems all subscribing to each other, you can imagine how you can use something like this. Each of these, you can reason about how caught up is that system, what time is it up to for a bunch of different data sources. So I'll go through, depending on people's backgrounds, I'll go through a simple example of how logs are used in systems, and kind of give at least an analogy to how we use these in some of the systems that are running at LinkedIn. In order to kind of motivate this example, I'll give kind of how to make a fault-tolerant hash table, since this is a popular thing. And to make it concrete, we'll keep CEO names in our hash table. To motivate this example, I'm basically trying to do a series of updates. And I want to kind of end up with this final state, which is for each company name, what's the CEO, right? And if I'm doing this in a single process, this is obviously very simple. If I'm doing it across machines, it's more complicated. And so I'll go through kind of how can you keep two machines in sync off of this sequence of updates. And so an easy way, one of the easy ways is a log, right? So if I log each of these updates to my hash table, I can feed these against both replicas. I can reason when I'm querying what's the state of my hash table, how caught up is it? So I can reason about how visible my data is. If one of these fails, it can kind of replay that log to come back into shape. And so this starts to address some of the problems of distribution. This is not a new idea. This is a very old idea that's existed in systems for a long time. The only difference, I think, is now, in addition to using it as an implementation detail of systems, we're also using it kind of in the large, where you have some central commit log that's applying to these external systems that are replicas of data. As it happens, we end up also using this internally as a way of building our systems so that our search system and our social graph system, we have a bunch of these kind of data stores. They're actually built in this way as well, right? Each of the nodes is subscribing to some of these partitions, keeping a local index that's good for certain types of queries, and then answering queries against this. Yeah?
What is that reads on the left side on the console?
Yeah, so I mean, I guess this is how you are maintaining reads and writes across replicas. So reads, maybe if it's our hash table example, it's get. And
so these are the replicas of your queries on log.
Yeah. This is kind of how you can use a log to provide some kind of consistency guarantees over machines. Okay, so now let me apply this back to this data integration problem. Let me give a concrete example. One of the things LinkedIn has is jobs. So there's a bunch of jobs on the website. When you start out, the logic for displaying a job is very simple. You kind of get the job out of the database and you show it to the user. But over time, actually, what most companies do with data becomes more sophisticated. And your display of a job actually gets a lot more complicated. In this example, I actually think I gave a subset of the total set of things that happens when somebody views a job. So that set of things would be, well, we monitor this, right? So if our job views is important, if that drops, we want to know that something is bad. We do recommendations for jobs. We recommend them to people. And so we actually keep track of what's the click-through rate or the application rate for individual jobs. So we can say, oh, this is a good match for this type of person. So that system needs to know whenever somebody views a job. We provide analytics to the people who post jobs. So we have to be able to show them like, hey, you posted this job. This is the number of people who looked at it for whatever much money you spent. There's a security team which kind of analyzes all this type of activity to make sure we're not being scraped or spammed or abused. So anything that happens there is going to get analyzed. And finally, there's kind of a data warehouse. And so you can see like this is one example of that data integration problem. Each of these systems has to be updated. If the system that was responsible for displaying jobs had to update all those systems and doing so correctly and making sure you have the same information available everywhere, it gets very complicated. The way in practice they do that is they would publish an event. It contains all the information. It says, hey, a job view occurred. This is all the information about the job view. This is the time it happened. This is a job that was viewed. This is the person who did it. This is what you need to know. And all of these other systems subscribe and apply that change. And so you can kind of see this is similar to that, logs inside a distributed system, but it's now actually across a bunch of systems. So you can think of this as a kind of central commit log for the data center or wherever, where you're journaling out updates and you're applying those across different systems. And I would claim that this is actually a lot better than what most companies do for data transfer. So depending on how much people know about that, it's sort of the dirty secret of how large companies ship data around. It's mostly a bunch of like CSV dumps, R-syncing files around, periodic jobs. It's kind of a murky thing to reason about whether it works or not. The advantage here is, okay, first of all, it's real time, so you get updates quickly. It can be, I think, comparably high throughput to the kind of file copies people are otherwise doing. And you can kind of react and process at the rate you want. You can also, do it in batch and do a batch load into a data warehouse. So it has the same kind of advantages, I think, of an offline ETL cycle while allowing faster stuff. So finally, I'll talk about one of the things that we also got out of making all of our data available as real-time streams, which is stream processing, right? This is kind of the ability to react to each of these streams and compute something on the fly. So it's kind of an interesting question why more things aren't done this way. I can give kind of one example from our experience, which is when I first got to LinkedIn, a pretty cool company called Truvizo came. And I think this was based out of maybe Telegraph CQ or one of the early stream processing systems. And they came to sell us a stream processing engine. And we were actually pretty enthusiastic. We thought, OK, this is really cool. We're going to use it. And at that time, when I had first got to LinkedIn, we had no real-time data. So we took the system and we were like really looking for anything we could hook it up to that we could run real-time queries against. And of course, we found nothing. And the best we could kind of come up with is we could take our hourly log files and we could feed them into the stream processor at the end of the hour. But then we spent a bunch of time and we built Kafka. We got everything going in real time. And then actually, it became very pressing. Once all your data is available in real time, you want to process it in real time. And I think this is actually a fairly general thing about how companies operate. So this is the first US census. And if you ever talk to a software engineer about the census, one of the questions they have is like, why do they just go around every 10 years and count everyone like going door to door? Why don't they just like journal the births index and keep like a running count all the time? But it actually makes sense why they don't do it that way, right? When they started doing censuses, they were doing it on horseback, with large binders. So you literally had to kind of do this batch collection. And I think this is actually not a bad metaphor for how a lot of companies' IT situations started, where you have a bunch of systems that are kind of loosely connected. You're kind of periodically shipping data out over, finicky networks. As things become more digital, as there's less people involved, I think it's very natural that large glump of data that's dumped periodically gets smaller and smaller, and you end up with a stream that you process. My view of how this works is pretty shaped by what we did at LinkedIn, which is basically we take these logs, we apply jobs that transform the feeds and produce new logs of changes. And so we ended up with a pretty rich ecosystem of things that were taking these feeds of activity that were happening, transforming them, counting, filtering, whatever, and producing new feeds of transformed data. Those transformed feeds, of course, would get fed into all the other things that data fed into. So like derived serving indexes, the offline Hadoop cluster, the metrics and graphing system. So this becomes kind of the transformation layer in that big interconnected picture. And when I talk to people about this, there's kind of a perception that stream processing is kind of this kind of weak niche. You can't quite get the right answers. It's all kind of approximate. And actually, that's not true. The stream processing frameworks that are out there today are a little bit immature, but there's no particular reason that this model of computation has to be much weaker than the batch model. So actually, it is actually possible to move a lot of the things that happen kind of on a daily cycle in companies to be much faster. You can get correct results. You can handle all these things. The fact that it hasn't all been done that way doesn't mean it can't be done. And the examples where this is particularly compelling for a website like LinkedIn is really monitoring. This is kind of how do you keep track of what the heck is going on across all these computers and different business metrics, and why is it working or not working. Anything around security These are both domains where you want to react very quickly. Content processing, if you kind of go in and update your LinkedIn profile, we go in and we try and figure out, okay, you said you worked at this company, is that correct? Maybe that maps to this standardized company that everybody's a part of. Kind of all the data normalization. A lot of the recommendation systems, especially anything that's dealing with click-through rate data, the kind of news feed of updates that come in and tell you, oh, these are the people who changed jobs. And finally, some of the processing that happens as part of the ETL pipeline. So all of these are actually pretty naturally suited to lower latency stream processing versus a kind of daily batch cycle. And there's a couple of frameworks that are out there that can help. There's Storm, and we worked on one that was called SAMSA. Both of these are pretty well integrated with Kafka, so you can take these feeds and kind of transform them and produce new outputs. The way SAMSA works, it's basically a layer that works on top of Kafka, and Yarn, which is kind of part of the Hadoop ecosystem and allows you to kind of run processes across lots of machines. You have a cluster like this. You can run a bunch of jobs that are doing these transformations and producing data back out to Kafka. And using that, you get this kind of integrated architecture where anything that is kind of produced as data comes into this kind of central log. The stream processing can transform it into some other log. You can get kind of monitoring or warehousing or key value storage on top of it. You can index it in your search system, et cetera. You get this kind of very well integrated picture. And that's what I had. That's basically the kind of Kafka SAMSA pitch. There's a more detailed write-up on this. There's also, actually, I think they turned it into an O'Reilly book. If you want to kind of dive into more details, I also, in that, go into more details on how you can actually build the kind of derived serving systems we had off of these log-structured data stores. So if you're interested in that, that's kind of a niche for people who are interested in building distributed data systems. But that has more details on it. And I'm happy to answer whatever questions people have.
Go.
Question?
Yeah. So when you're talking about real-time, multiple producers, consumers, how do you make sure that the streams gets consumed when they have different rate of processing opinion, right? And where would this data be buffered in some way? Just it's much slower than other consumers.
Yeah. So the question is, let's say you have many people producing data. And then you have different consumers that are operating on different timescales. Like one is very caught up and the other is very far behind. What happens to the data that is not yet consumed? How does that get buffered? So that's basically what Kafka does. It basically acts as this giant buffer. So go ahead.
It's all memory?
No. So let me talk a little bit. I've kind of glossed over how Kafka actually works, because this is more like how to use it. What is it good for? Which is maybe the more important question to answer first. The way it works, the way Kafka works is it literally maintains a log file on disk. Okay, so every time a write comes in, it writes it to this log file, and that log file is replicated across machines. So when a write comes in, it writes it, the write replicates, we acknowledge back and say, oh, we got your write. And so like the amount of buffering space you have in a Kafka cluster is the total disk space of all the machines divided by the replication factor you're using for your data. So if you're using replication factor 3 and maybe you get 5 terabytes per machine, you have 10 machines, then you got 50 over 3 terabytes of buffer space. And so in fact, not only do not all your consumers have to be totally caught up, you can have consumers like a warehouse type consumer that just pops up once a day, sucks down the daily ETL load should you choose to run your ETL on a daily cycle, processes it, and goes on its business. And that's actually kind of one of the primary things you need. It actually turns out to also be really important for stream processing. The reason being, okay, you would think stream processing, it's all real time, they should all be caught up. Yeah, I mean, maybe, right? But this is a company full of people working. Somebody's thing kind of breaks down or slows up and can't keep up. You can't have everything kind of backing up and the whole data flow processing graph grinds to a halt because one guy, checked in a bug. So that buffering capability is extremely important.
On a company-wide scale, what's the data generation rate would you use?
That's a good question. I think I had some stats which may be slightly out of date, but I think we were claiming we had about 175 terabytes of in-flight per day, so that would be 175 terabytes of new updates or whatever. And I think that that is probably the compressed number pre-replication. I guess if you multiply, if you count each write 3 times, then I guess it's bigger.
What do you think is the average size of the record?
Yeah, okay, question is what's the average size of a record? It actually varies a lot. So some of the records are very small. They're just a few IDs, like this person did this thing at this timestamp, da-da-da, and all the things are normalized, so you just refer to them by ID and it's very tight. We're using something called Avro, which kind of helps shrink the data down. Other things are actually these incredibly large records with lots of key value pairs describing all kinds of context around what was happening. So it totally depends on the type of data. So for example, application error logs tend to be very verbose with like huge error stack traces and error messages and whatever. Other things tended to be very small. It's basically, this was an open system. So in the end, there was actually probably well over 1,000 of these topics of data created by different people. And so it kind of is whatever somebody put there.
So do you normalize data at all before it receives Kafka, before Kafka receives it, or do you do that all after when you consumers are working on it?
Yeah. So
or if you
yeah, the question is like, what kind of normalization is there for data? The way it is usually convenient to write stuff is usually by IDs. Usually whenever you're working with data in one of the applications, you have the ID. So you have a user ID, maybe a job, you have a job ID, a geography has an ID. Everything has an ID, right? So you would probably be writing out those IDs. If you want to get back any more attributes about that thing, you have to join it on, which is what people what happens in the stream processing layer or offline in Hadoop very commonly.
So you read from other databases, add information.
Yeah. So
yeah,
this is actually an interesting design point. So it's very common that there's a lot of debate. So the people who process data, they typically want you to add everything in for them so that the feed has everything. The people who generate data usually don't want to do that because it's slow and a big pain in the butt. And so there's some debate over what makes it into the event and what doesn't. I'm not sure what the right answer is. I mean, I think if you find yourself, like we had situations where someone would be like querying the social graph to find out distance information, to figure out some distance to put in the logging event. That's probably not really required. You're like slowing down the site, right? Like probably that should be done offline. So I guess usually the principle is do it offline if you can. But sometimes there's things that are just so convenient for analysis, you might as well just stick it in. I don't know that there's a hard and fast rule. Other questions?
I'm trying to understand the size of this cluster with so many reads and writes happening per second with the latency of 1.5.
Yeah, no, I think the latency, I should say that this is a mixture of observed and performance test data. The latency is probably more a performance test result. The actual observed latency depends on 3 things. It depends on the buffering in the clients. It depends on what data center you're in because we replicate asynchronously between data centers. So depending on the amount of buffering, it can be higher. That's really just the time it takes with no buffering to do a write, have it replicate out to 2 replicas, and have the consumer process together.
So in this case, this is for data center, like per colo is per...
Yeah, no, I think the size data is probably overall, and I think that the writes and reads per second, I think, are probably also overall. I don't think those are per data center.
But it appears that the cluster will run into thousands of nodes. Or?
No. So yeah, okay. Question is how big is a Kafka cluster? So I guess we had 2 things that were usually actually pretty closely related. One is Hadoop, and the other is Kafka. The reason they're related is because everything that went into Hadoop pretty much came from Kafka. But they're not the same size. And the reason they're not the same size is because Kafka is just keeping data by default for a week. And then some people would set it to longer so that they could replay off of that. But it's not keeping it forever, whereas Hadoop was keeping 2 years retention. And that pretty much determines the size. It also the processing model is also really different, right? A stream processing engine is much more efficient. It mostly just keeps up with the live stream. So if you process a year's worth of data in a stream processing system, you do it in a year. If you process a year's worth of data in a batch system, you're usually trying to do it as quickly as possible. And so the number of nodes in an offline system ends up kind of ballooning up because of that. And so I think we had thousands of Hadoop machines total Kafka footprint was like maybe 300 machines, but by no means, the reason for that was like, oh, we would have a cluster for each acquisition because they're in different data centers, and then we segregated operational data from business data, and so that led to different clusters, and then you need a cluster, and so like it kind of counts up, but like probably the individual sizes of the clusters was like 20 or 30 nodes, something like that. They're not huge.
So let's assume 300-400, whatever it is. So essentially, it's handling maybe 100,000 messages per node per second.
Yeah, that's probably reasonable. If you think about it, this is like a throughput-oriented system, so it's pretty easy to get good throughput. Like 100,000 is not really that much when you kind of like multiply it by bytes and turn it into I/O. Yeah. Question.
I read on your blog that you're using it on real hardware instead of virtual machines.
Mm-hmm.
Can you talk a little bit about that and what the performance implications are that you found?
Yeah, sure. So the question is, you guys are running this on real machines, kind of why, and what are the performance implications? So we, LinkedIn is not in AWS. So we run everything on real machines. We have systems that kind of deploy software out to everything. So I guess there's some level of elasticity on the machines you have, but there's no like, KVM or Zen or something layer. In fact, it doesn't really make sense within a company that you would need that, like virtualizing the OS. You kind of are all using the same OS. At a certain point, yeah, you realize, oh, we're running 20. Yeah, I don't know. So yeah, the question is, I guess there's a couple ways you could ask it. Like, one question you could ask is, why isn't LinkedIn in AWS? Another question you could ask is, does Kafka work well in that virtualized environment? It's a bunch of different things. I mean, basically, at a certain scale, you kind of want to pay attention to efficiencies, and you can probably do it cheaper yourself. I guess LinkedIn's probably at that scale at this point. I know we did some cost stuff, and it was basically cheaper.
Yeah, well, with us, it's more like the data center is just built that way. It's our own, but they they have machines and they carve out certain chunks of it. The machines are just so big, quote unquote.
Yeah.
It doesn't make sense to just leverage a full machine for one node.
Totally.
And so the question is basically, at what point, if you did you see that it just made sense to go onto real hardware versus staying on?
Yeah. Okay, so I can answer that both ways. So LinkedIn and other web companies, they have the opposite problem as what's typically solved by virtualization. Typically, virtualization is like, we have way more applications than machines, so we want to shove a lot of applications onto one machine. I think most of the web companies actually have the opposite problem, which is they need to actually scale applications over large clusters of machines. So they're doing like the opposite thing, which is managing applications over pools of hardware. And we have some internal stuff to do that. I guess there's systems out now like Mesos, which are meant to be kind of general purpose solutions to that. The Kafka will actually run quite well on AWS. I think there's a number of the biggest Kafka users are like Netflix, Pinterest, whatever, and are totally doing it that way. You do take some I/O hit with that type of virtualization, but it's not very large. One of the things we paid very close attention to is, since we're just keeping a log, we are doing really very simple linear I/O. It's kind of the simplest possible I/O model. It works with old-fashioned spinning Rust disks, and it doesn't suffer terribly by virtualization. They seem to have some weird things, like the first time you write in AWS, you pay some penalty and whatever. But so you definitely take a hit, but it seems to be totally fine to run. The people who run there don't seem to have any big operational changes in how they run it. Other than the interesting thing is they actually choose to run much larger clusters on smaller hardware because the cost of losing one is less. And I guess you can. So that was the only major difference I came up with from looking at their setup and ours. Question?
So in your example slide, which is, I would say, other use cases for Kafka, right? So you have monitoring and security, which are also the sweet spot of Splunk and some of the other logs management.
That's right.
So how would you compare this solution to the well-known Splunk-based solution?
Yeah. Okay. So the question is, how does this compare to Splunk? Which is a good question. This is a much more platformy approach. So the good news about this is it's like this open piece of infrastructure everything can plug into. It's open source, etc. Splunk, I think, did a great job of putting together an end-to-end pipeline with a search engine on the other end for really text logs, right? And they've kind of branched out to other stuff. I think the thesis I have is that this kind of like log or event data is really an important thing. And so the way you get started, of course, is with a kind of vertically integrated pipeline like Splunk. But I think the end result for companies is they'll have something that's more general purpose that cuts across different data sources and plugs into more outputs, allows richer processing primitives and so on, rather than a proprietary vertical pipeline. Time will tell.
And in terms of performance, let's say the same kinds of logs that are coming into Splunk versus Kafka, how would you?
Yeah, I mean, so I would describe Splunk. The question is about what's the performance of Splunk versus Kafka. I mean, Kafka is basically a log, and so it's very fast at logging data. If you want to get a good performance summary, this is more like production data, but we did do a good performance blog. If you Google for like Kafka performance or whatever, there's a reasonable rundown of like, okay, with different replication levels and acknowledgement guarantees and so on. But Splunk's focus has actually, I believe, been more on indexing and search. And so, unless, a multi-subscriber log to fan out to other systems, right? Mostly they want you to fan it into Splunk, and they have some hookups to Hadoop and a few other things. So I guess their performance is, I think, and we were a long time ago, we were a customer of Splunk. At that time, their performance was very driven by indexing speed of their search component. So I don't know that it would really make sense to compare their search indexing, which is probably a much more expensive operation, with the fast, cheap logging that we do.
Well, my question would be more than, once Kafka has the logs, there's some processing that needs to happen in case of Splunk, it's search indexing.
That's right. That's
what
right.
application is there on top of Kafka.
Yeah, that's right. That's right.
So then how would those?
That's right. Yeah. So an equivalent thing, if you were trying to make an open source Splunk-like thing, that would be something like Elasticsearch or Solr, which are the kind of open source, search things, very commonly used with logs. And Kafka would be a sort of data pipeline for that.
And along the same lines, you have recommendations as one of the examples.
Yeah.
How easy or good that recommendation engine would be to do it on top of streaming versus offline?
Yeah. I put recommendations. That's more a family of different types of applications than it is an application. We built a bunch of different recommendation things, and there's a bunch of techniques that all work differently. So we had batch algorithms that would recompute periodically. We had things that were click-through rate based, which I think is the best match for this kind of streaming stuff where you're looking at what's popular now. That's really probably the best fit for this kind of streaming model is what's popular now, what's trending. You basically take the attributes of the user, you pool click-through rates or whatever by those attributes, and you do some modeling based on that to roll it up. The areas where that makes sense is like ads, news, things where popularity and freshness matter. Anything where there's no freshness component can just be totally done offline. So for example, we do similar profiles. If you go to somebody's profile, it has a long list. That was something I worked on a long time ago. That's totally done offline. It doesn't change that often. Like people aren't becoming similar to each other or dissimilar very quickly. So it gets recomputed like maybe every day or something. And there's not that much value in making it faster. Question?
Would you recommend the system for something that's not, say, a social network website, but say a sequence of nuclear reactors that are all, again, have data logs and error reports and the same sort of things, except on a different scale?
Yeah, possibly. I don't know anything about the application, so
Invented, or a sequence of ground stations that are totally.
So something similar to this is actually very similar in a lot of finance companies, like financial services. Anybody who kind of who has to come into this real-time domain very often ends up with a similar thing where you have some kind of log and you have a bunch of things that feed off of it and you have replicas of that. I actually think it's actually a pretty good general way. I've used a lot of like social network examples because I know them. But yeah, I think it is pretty general. The things that have to be true for this system to make sense is your data has to be record-oriented, which is not always true. So if your events are like genomes or something, they're probably pretty big. They don't really make sense as events. This is really like things happened, the things are, records, they're happening really quickly. Our data model is like the world is streams of records. So if you don't have records, this probably isn't a good fit. And then you would have to get some value out of the processing things kind of as they occur versus at least some scientific computing applications. Maybe you just have a big pool of data and you run some cool algorithms on it and you get the result, but the data isn't really changing as quickly. So I don't know if it's a good fit for that, but yeah, it definitely has found usage in like a bunch of non-web companies, so like telecom companies, finance companies, and so on. Cool. Question in the back.
A couple of questions come to mind around just your vision of the future and the ecosystem that you'd like to see emerge around this. For example, an app store of producer and consumers, and we kind of standardize on a bus. Confluence, is that the name?
Yeah, Confluence is the company. That's right.
Do you see that as being a steward for open source in the Docker sense, or do you see that going as in the Kinesis direction of Kafka as a service?
Yeah, so one of the early things, I guess the question was, what's the company doing? Well, I mean, we're just getting off the ground, so we're still figuring it out. But another question was, what about all these different plugins to connect different systems? Yeah, being able to make those work in a standard way, have a common data model across them so it's easy to plug things together, that's kind of like super low-hanging fruit thing we'd like to take care of. Any other questions?
Did I hear a company name at any point?
Yeah, the company name is Confluent.
Okay, Confluent. And what was the motivation to start? I mean, my question when you came in was, why isn't this a company? But why is it a company?
Yeah, so the question is, why is this a company? The answer is, we thought this was basically a much better way of organizing your data than what most companies were doing. And we thought it was not totally feasible to get everybody in the world to do it via an open source project. You can kind of get a certain amount of the way where people who are very technically sophisticated, have a large team of engineers to throw on it and adopt things quickly, will do it. And that's kind of the state we're in now. But to get the rest of the way, I think it actually requires more money, it requires more support, and so on. So the mission of the company is basically to make this real-time data stuff work, right? To make the data flow and data integration problem work this way, replace the kind of rsync batch files, make stream processing a reasonable way to consume that data and transform it into other things. That's what we're trying to accomplish. And the reason for the company is just because you can only go so far on GitHub, I guess.
So it's like Hadoop, Cloudera, that sort of thing?
Yeah, that's right. Yeah, we're not looking to do any kind of hosted Kafka. I think this naturally lives wherever the rest of your systems live. So if that's in the cloud, then you would run it in the cloud. But if it's on premise in your own data center, then it's in your own.
Say IBM Consulting, you've got these problems. We will make solutions for you and give them back to you.
Yeah, that's right. We're not really doing heavy consulting. We're going to kind of take this package and put together a set of things that people can use. Product services.
In terms of the processing infrastructure on top of it.
Yeah.
So you mentioned about stream processing on top of it. So what kind of modules or components do you anticipate in this package?
I'm not sure. We basically just announced the company like 2 days ago, so we're still figuring it out. Question to that.
So I've read the data bus paper, and I've been curious. Is that Kafka?
Yeah, it's actually, so there was, the history of this is there was actually a system before Kafka at LinkedIn that was virtually identical in the abstraction it provided, and it was called Databus. And the caveat on it was it only worked with databases. So it would basically acted as a sort of cache for whatever the database log was. And it was used in this way. And then basically we liked that so much. It was built originally to feed like the social graph and search. So it was like very, very, very straightforward. We had relational database, we had a social graph, search system. They each had a bunch of machines. They had to be fed changes. We built this like cache for the log. And we fed it out. And then we were like, oh my God, this is the best way to feed changes around. Everything we're doing is basically feeding changes. And in particular, we were interested in extending that to event data. This is the page views and the clicks and the impressions and that kind of stuff, which is much higher volume. And obviously, there's no upstream log of that to act as a cache for. So that was what we made Kafka for. Originally, it was just used for that. It's now kind of expanding out to all the use cases that were originally data bus.
The interesting thing that with the data bus paper was the idea that somebody could bootstrap from ground zero the whole background thing.
That's right. That's
which is something that I guess is not really part of Kafka because Kafka just keeps it for a week.
Yeah. So that's a good question. Okay, so this is a nuance. We had two systems, Databus and Kafka. Databus was the earlier system. One of the features of Databus was it would allow you to kind of go back to time zero, and it would kind of filter out redundant updates for you. And that was actually very nice. You would think, well, why would you want to do that? Turns out it's very useful if you have something like a search system where you have a bunch of nodes which are subscribing to some part of the log and indexing it. If you lose one of those nodes and they lose their data, the most natural way to restore the data is actually just to say, hey, that node is at time zero. That's its time. And it just kind of like plays forwards and reindexes. And so we actually do have that feature in Kafka to be able to kind of prune obsolete updates in a similar way. We call it log compaction. And it's specifically used for that. Because Kafka also takes writes, you can actually use that for all types of interesting journaling of computation use cases. We use it in the stream processing system to be able to do stateful stream processing, like maintain counts. And all of those updates are journaled out so that if the stream processing with one of those instances fails, it can kind of restore itself from that log. So actually, it's a very cool feature. I didn't go into it in detail here just because it's sort of a more advanced topic, I guess.
I'm curious on high availability.
Yeah.
Achieving 5 nines while simultaneously adding more hardware, resharding, just keeping things going without interruption to the stream.
Mm-hmm. Yeah. So the question is, I think just generally high availability. How does it work, right? Okay. So this is a fairly traditional like master-slave model. So at any given time, the cluster has a bunch of partitions, maybe 1,000 partitions that cover all the different topics. Each of those partitions has a leader and some followers. And the leader accepts all the writes and determines the order. The followers apply those writes in whatever order the leader determines. If the leader fails, you elect a new follower out of the set of followers that are in sync and available for election. So the guarantees you get out of that are your non-availability window is going to be the time it takes to detect that the leader has failed, and then the time it takes to re-elect a new leader during. So whenever that failure happens, you have a small window of write unavailability. Usually for this kind of system, it's okay. Like the producer can kind of buffer and keep writing as long as it's very quick. Where you would run into larger problems is if you had some kind of like persistent network partition. That mostly doesn't happen to us inside of data centers very often. It does happen between data centers, but we would always run these clusters in a data center and kind of replicate asynchronously across. And so that problem is less of a problem. That is the kind of, that's how the fault tolerance works. Maybe your question is more like, what's important to run it and keep it available?
Yeah, there's an operational side to it.
Yeah, that's right.
So Kinesis has this concept of resharding, which kind of exposes their implementation to a degree. And you mentioned there's some parity in the APIs. I'm just wondering.
Yeah, that's right. That's right. Yeah, so Kafka doesn't do resharding. You can add partitions, right? But we don't do any kind of transfer of data if you do. So if you have one partition and all your data is in that partition, you can add another partition, but then you have one partition with a bunch of data and one partition that's empty. Presumably your writes will now distribute over those two, but we don't reshuffle the data, if that makes sense.
So over time, this partition will be
made
and then.
Yeah, I should answer that. So our model is basically an over-partitioning model where we say like, okay, if you think you want to scale eventually to 100 machines, you need 100 partitions. Now, of course, some people underestimate what they need, and then they do. But when that happens, you have to, if there's really two cases. Sometimes the partitioning is used really just for scalability, and sometimes it's used as a kind of semantic partitioning, where you're partitioning by key, and the stream processing system that is subscribing is partitioning up its processing along with that. In the first case, it's easy, right? Now you're just distributing over more shards. In the second case, it's actually hard, and resharding that data is going to depend on the semantics of how you're using it, and that's something like you would have to participate in. All right, any other questions? Back.
What are some of the things you see need to be done in Kafka to make it more widely accepted in the big systems?
Yeah. So the question is, what's needed in Kafka to make it more widely accepted? Couple things like security. Like right now, we don't have any built-in security. That's a big deal. The maturity of the clients outside of Java. There's a long tail of clients, and really getting something that's robust in every language is important so that it works with whatever language people are using. And I think just the kind of out-of-the-box experience, like we've done this as an open source project, so we kind of give you this pretty reliable piece of low-level infrastructure, but everything to plug into all the rest of the systems is something you would kind of do yourself. So it's a lot of work now to actually adopt this in the company and put it to use.
Any concrete ideas for tooling on Kafka to make things easier? I mean, there are command line tools today, and probably people at some point want to see a console and an interface that they can do things. Is this part of your charter for the new company, or?
Yeah. So the question is, is the company going to do anything to make tooling for Kafka easier? The answer is yes, probably, but I don't think we know exactly what at this point.
One other question I had was about the example you took of TrueViso, which is more of a stream processing engine, and Kafka is more of logging, buffering engine. So those are two different solutions. So I guess what you're trying to achieve with TrueViso would be very different from what you can achieve with Kafka. So what was the vision around deploying TrueViso?
So I gave this TrueViso example at LinkedIn. I was kind of trying to motivate why. I think the point I'm trying to make is I feel that like step one for us was actually making data available in real time. And then once you have that, you very much want to process it in real time. It's very hard to process data in real time if you don't have anything available in real time. That was really the point I was making. In this model, there's really two things, right? There's a kind of real-time stream, and then there's like a processing engine, which would be the processing point. In TrueViso, it's obviously more combined, right? You could argue whether or not this separation of the stream processing layer and the kind of underlying log is good or bad, but that is how it is. The processing layers people use commonly are like Storm, Samza, which I talked about, and a little bit Spark, which has some stream processing stuff, all of which integrate pretty well with Kafka. Cool.
So building these large systems is still sort of at the stage of trying to figure out what all your pieces are, and then scurry around in GitHub and various companies in the Valley and pick up tools and make things. Mm-hmm. When is somebody going to figure out system integration for large scale systems as a product or as a company?
Mm-hmm. Okay, so the question is, it's very hard to build, these types of large-scale systems. I don't know if you mean individual components, or your other question was more like integration between components.
I mean to build LinkedIn.
Yeah. I think hopefully this helps with some of the data integration problems. I mean, what we found to be a simplifying abstraction was being able to take data across many different things and make it available in a uniform way, right? That obviously helps. There's other parts to that. So like there was a bunch of tools we had specifically around building distributed systems. That's kind of use to people who are building distributed systems, but it's not necessarily as related to the data integration problem. I don't know. I guess I had this discussion with a friend that maybe all the hard problems are integration problems, because just the nature of software is anything that's you can turn into a reusable abstraction, you've done it. So once you have all the reusable abstractions, all that's left is integration.
Yeah.
So maybe the nature of it is it's always going to be integration problems. It's just that the type of integration problem will change. I don't know.
Cool.
I guess I have a quick question. Yeah. A question on data retention. Again, going back to Kinesis, it's a 24-hour retention.
Yeah.
You mentioned time zero with the data pipe. Given there's this race to zero in storage, Dropbox, Box, and these various players, if you extrapolate out storage over time, do you foresee within 5 or 10 years we could infinitely retain logs? Does that open up new machine learning or that kind of corpus of data?
Yeah. So the question is it reasonable to infinitely retain logs? Yeah. The answer is yeah. Absolutely. There's the retention is configurable. If you configure a bit to infinity, then it will retain forever. Usually, people don't actually want to reprocess everything, but it can actually be useful. The model we've taken is, we use Hadoop as kind of the archival store. For LinkedIn, I think most things just go back 2 years. It doesn't go back to the beginning of the company. You could argue whether that's good or not. And then we use Kafka really for the stream processor, for kind of reprocessing in these stream processing jobs. And so there are some topics that have much longer retention or use that kind of keyed compaction to give you a complete snapshot for the stream processor to be able to restore its state. So why would you want your stream processor to go back in time? The answer there is usually like you change the logic in the stream processing and you want to compute it some different way. It has to kind of restart and reprocess.
Yeah, think of forensics audit, for example, is usually post facto. Serving SOX compliance, retention of 12 or 13 months of logging into every single system, then having to go back in retrospect and analyze the logs. And that's a huge IT problem today with distributed systems, distributed logs.
Yeah, so the question is like, would this be useful for an audit of historical logs? Yeah, potentially. I haven't heard of that use case, but absolutely.
Adding to that one, so the size becomes huge. Is there some kind of compression that goes in?
Yeah, so Kafka does have internally a kind of batch or block compression that compresses together records, which is very important, especially for these text-heavy records, for getting good compression.
So going back to the question that was asked earlier around integration in large systems, right? So these corporations which have multitude of systems talking to each other and individual connections, typically will have some ETL tool in the middle trying to transform it, or Informatica or something else. So how easy would it be for them to replace that, plug this in, and what kind of support will Confluent be able to provide in that regard to take that transformation, which comes with its own store as well, so that the in-flight data can transform, shift around, versus.
Yeah, so I think the question is how good of a replacement is this stuff for an ETL tool today? I think the answer is it kind of depends. What the ETL tools really do a good job of, I would say today, is they have a pretty rich GUI which allows you to kind of model all the transformations, and then they kind of carry that out in their system. What this does, I think, a good job of is, or what we did a good job of, at least at LinkedIn, and what we'd like to make easier for other people to do, what some companies have done, is actually do a good job of capturing structured data, capturing good metadata along with your streams, and being able to kind of like directly mirror that in something like Hadoop. What we found at LinkedIn was, if you do a good job of that, you can actually replace a lot of the more mundane data cleanup problems because your data is well structured to begin with. You can get rid of a lot of the manual work in data loads because Hadoop is actually pretty scalable. So you can just have a rule that's like, hey, everything that shows up, we load. And we turn into a Hive table. We use the metadata to create the Hive tables. That doesn't get rid of every type of transformation. There's actually a lot of high-value transformation that happens later, but it becomes a subset instead of it being the case that every piece of data has transformation along with it. I think if the stream processing layers, if these kind of open stream processing layers become more sophisticated, I think it'll be more possible to replace all of it. But to a certain extent, like transformation of data is kind of the mandate of almost every tool in the Hadoop ecosystem. Like there's like 47 transformation tools and languages. And so one critique I have of ETL is like, well, E is extract and L is load. E and L are pretty mechanical. T is actually like all of programming. And so you have to be specific about what part of T you're actually trying to capture. All right, cool. So I'm happy to take other questions if people have them up here. But thank you all so much.